In this video, we're going to be talking about how to analyze infrared spectrum. So in infrared spectroscopy, the main things that you want to be looking at in the spectrum are the wave numbers. So here you have in the scale, wave number is that, and wave number, remember, is defined as frequency over the speed of light constant. So in what you have, this is what you have in the x-axis, and in the y-axis is transmittance. And notice that we have things that go almost all the way down, as you can see here, and that is close to zero transmittance, which means that's almost all the radiation was absorbed. That's what it is. And so this is why we call these absorption bands. Although you can also find a spectrum where the here is absorbance. Most spectrums we will see here are with transmission. So absorption bands. First thing that you want to be looking then is where are the bands, so the wave number. And as for an example, to better analyze, let's draw a line here, 1500, and I'm going to do another line. Well, I try to make it straight in 3000. Anyways, so what we're going to be looking at is this region, which we call the diagnostic region, and under that is the fingerprint region. But mostly we're going to be doing in the diagnostic region and learning about functional groups. That's the most important information that we're going to get out of the IR spectrum. And so that's the first thing that you want to be noticing. Where are the bands? So this particular one is broad. That's an alcohol band. But it is, say, starting in 32 up to 3600. So that's what we say the wave number. Where is the band? Then we're going to be looking at the intensity. So there will be bands that are large, so a lot of absorption, and some that are small. And the other factor is shape. So whether the band is like narrow or broad, like that. Because those are important characteristics that will help us determine functional groups. Okay, so you divide your spectrum in these regions, and we're going to be talking about 1500. And in this diagram, we see again the scale of wave number, and this is where you are your 1500, where I did my line, and then I have 3000. And I do 3000, but it's still the hydrogens attached in this region. Anything hydrogen attached to carbon of different types, or to nitrogen, or to oxygen, are going to show up in this region. But it goes all this for the bonds to H, and then we will have the region with the triple bonds and the double bonds, all of these. But we're going to see difference in both in shape and intensity for all these bonds. So talking about shape and intensity, here we have some examples of functional groups. The first functional group that is here is carboxylic acid. And two things are characteristics of carboxylic acid. When you go and analyze, I'm going to redraw the structure in a different way. And the band is very broad. As you can see, this goes like from 2300 to 36, 35, 36, so very broad. And sometimes so intense also that it covers other bands. And the reason for that is that we have hydrogen bonding interaction. Well, my drawing wasn't that good. And anyways, you got the formation of dimers. And this is why. So double hydrogen bonding. I'm going to redo that again. And that's what makes the band so broad. So in Of course, carboxylic acid also have a band here, the carbonyl band, which we're going to find here, and that is a very intense band in about 1700. But there are other compounds which that have carbonyl bands. Examples of other compounds with carbonyl bands are ketone, aldehydes, with the carboxylic acid, of course. We will have esters and amides. They show in about the same region, but slightly shifted. For example, ketones that are conjugated show in lower than 1700, maybe 1650, and esters, for example, is higher than ketones. So let's say that we have 1700 centimeters -1 here, and for esters above 1750, so maybe 1800 or so. And this, we can say the conjugated ketone, always conjugation brings the band lower. For esters, so lower than this may be 1780 about, and so the conjugated ketone maybe in 1650 or so. These are not exact numbers, to give you an idea just where things are. So this is about compounds with carbonyl. So we have this distinct shape for carboxylic acid in the other band in 1700, say for all the carbonyl compounds. But there is one way, one very interesting band to distinguish between aldehydes and ketones, and it's this. So aldehydes have this hydrogen attached directly to the sp2 carbon, and it has another band besides the carbonyl, and this is in about 28 to 2700 centimeters -1. And that's how you can distinguish between ketones and aldehydes. So very important to know that. Now let's go to the following shape here that I have. This one is an alcohol band. So alcohols tend to have the shape, so somewhat broad, but not as much as the carboxylic acid. And again, the reason for that is that alcohols, when they are, say, in relatively concentrated solution, they will form hydrogen bonds. In always hydrogen bonds broaden the band. However, if you do have an alcohol, say, diluted solution in an organic solvent where you're going to have hydrogen bonding, you may be able to see this. And sometimes we can see the broad one and the more sharp one. So that is, again, hydrogen bonding is because you have this, right? When you see this broad band, it's because you have hydrogen bonding. If you see this narrow, then it could be when you have diluted alcohol solution. Okay, so distinct shapes that we need to remember. Going into the nitrogen-containing compounds. So let's say ammonia. Here we have it. So that's ammonia, but if I replace one of the H's by an R group with carbons, right? This is a primary amine. And primary amine has two H's, and therefore they have two important vibration modes, and that gives rise to this double band in, say, 3400 centimeters -1. So that shape is very characteristic. Typically, you will see one shorter than the other, like that. Now, if you substitute the H's in ammonia by R groups, now you have a secondary amine, and the secondary amine will absorb in the same region, but here you have only one band. So this is one important way to distinguish a primary from a secondary amine. If you have a tertiary amine now, so replacing the three H's in ammonia by nitrogen, now you don't have a bond in H, so that tertiary amine will not absorb in that region. Also quaternary ammonium salts. So here we have it. In now bonds to carbon, they also have characteristics. So if you do the line here in 3000, this is an alkyne. Notice the alkyne has two important things. The bond carbon-carbon triple bond in about 2200. And this is carbon attached to sp carbon, and at about 3200 or so. So above the, say, 3000 line. Also above the 3000 line is the alkene. This is the alkene, so carbon sp2 hybridized. A hydrogen attached to a carbon sp2 hybridized. And right under the 3000 line, let's say, is the alkane. So hydrogens attached to carbon that are sp3 hybridized. So here we have, say, important shapes that we're going to be analyzing to determine function groups. This is the line that I said that we always draw. I suggest that you do that. So you do your line in 3000, so it's slightly under are the alkanes. So this is your sp3 carbon. Slightly above 3000, you will find the alkene. So that's your carbon sp2 hybridized. And even more, a higher weight number is the alkyne. Now, important that you notice if the alkyne, for example, is internal, like this one, internal alkyne will not have this bond because it actually lacks a hydrogen attached to the carbon. So this signal is for terminal alkynes, which have actually that. So if it is internal, again, you lose that signal, but you will have the carbon-carbon triple bond, depending more or less intense, depending on the substitution. And here for alkenes, the signal with the H is lost in this structure because this is tetra-substituted alkene. But if you have this, for example, this is di-substituted, so you have two H's. This will give this signal right here. But this one will not, so no signal in that region because you lack up that. Okay, so later we're going to be analyzing now a spectrum using these features.